Good morning. Today we're going to quickly review what we talked about last week on waves, and then we're going to continue with calculations for speed of a wave. So you are going to need a calculator for today. So last week when we were discussing waves, we talked about the different parts of a wave. We talked about the fact that waves carry energy from one place to another, and that some waves need a medium or anything that has molecules in order to transfer their energy. Remember, a medium is anything that has molecules, so solid, liquid, or gas. Mechanical waves need that medium to be able to transfer their energy through from one place to another. Those are example of sound waves. So sound will not travel from one place to another unless there's a medium present, air, water, anything that's a solid. And then the way that the molecules are set up in those different states of matter is going to determine how fast the speed of the wave is going to move. So the way that the molecules are in matter determines the speed of the wave. And then you also have electromagnetic waves, and electromagnetic waves like light can travel through nothing at all. They can travel through molecules, but they can also travel through nothing. Okay. So remember, mechanical waves need a medium in order to transfer their energy. Again, this is like sound. So there's two types of waves. You have transverse waves, and then you have longitudinal waves. So usually when people think of waves, they think of waves that go up and down and up and down. That's a transverse wave. We also call those waves perpendicular waves because the energy is going from left to right, or right to left, sideways, horizontally, but the wave itself is going up and down. So if you look at the wave motion itself, which is going up and down and up and down, and the motion of the energy, they form a perpendicular. Okay, they form perpendicular lines, right angles. Whereas longitudinal waves are known as parallel waves because the energy again is moving side to side and the wave itself is also moving side to side. So think of if you pulled a slinky, if you pulled back on a slinky, it wouldn't move up and down. Okay, it would move and kind of inch along the length of the slinky. That's how longitudinal waves move. Okay, we talked about the different parts of a wave. So here's the way that transverse waves move. Remember, up and down, and then this is the way that longitudinal waves move. So those little dots you see are the molecules, the air molecules, solid molecules, liquid molecules, whatever medium they're traveling through. We talked about the different parts of a wave. So remember, for transverse waves, you have the crest, which is the top part. You have the trough, which is the bottom part, and that is all in reference to the equilibrium. So whenever there's no energy flowing through the medium, you're going to just see the molecule, the particles not moving, and that would be kind of like the straight line here. So when there's no energy flowing through, this is where you would have the wave, so zero energy. Once energy starts to flow through, then you're going to see the top part of the wave and the bottom part, which is the crest, and then the trough, push out from the equilibrium. That distance here that it pushes out from the equilibrium, that is known as the amplitude. So the bigger the amplitude, okay, the bigger the wave is, the more energy that wave is going to have. We talked about the frequency. Here, remember, frequency is the number of cycles per second. We talked about what a cycle is. So the easiest way to measure a cycle is a wavelength. Wavelength is easiest to measure from crest to crest or trough to trough, but it's really the distance between any two corresponding points on a wave. So if I were to pick this point right here, okay, I would I would pick the same point on the very next wave, and the distance from that point to that point, that would be a wavelength. Again, it would be the same thing as if I were to pick this point here, the top of the crest, to this point here, that would be a wavelength. If I were to pick the trough, this point to this point, that would be a wavelength. So frequency is how many cycles, how many wavelengths you have in a 1 second time period. Obviously, the faster the wave is going, the more cycles you see in a 1 second time period, the higher the frequency. Frequency and wavelength, it's key to remember that they are inversely related. So the longer the distance, the bigger the distance is from crest to crest, the lower the frequency is going to be. Okay, so the longer the distance here, the less cycles you're going to see in a 1 second time period. The closer the waves are together, the more cycles you're going to see in a 1 second time period. Again, wavelength, this is the Greek, they use the Greek letter lambda to represent wavelength. You measure wavelength though in meters, and then frequency is going to be measured in hertz. Okay. The speed of the wave, remember, the speed of the wave is dependent on the medium that it's in. The solid, liquid, or gas, the medium that it's in is going to determine how fast the wave is going to travel, how fast the energy is going to get from one place to another. The speed of the wave is frequency times the wavelength. Remember, frequency is measured in hertz, and the wavelength needs to be measured in meters. The speed of the wave would be measured in meters per second. Okay. So here are some practice problems. Remember, speed of the wave is frequency times the wavelength. Remember, frequency is how many cycles per second, and the wavelength is the distance of one cycle, or the distance from crest to crest, trough to trough, or any two corresponding points. So let's look at problem number 1. Number 1 says the wavelength for a wave is 23.4 meters, and its frequency is 103 hertz. What is the speed of this wave? So if you have your formula, okay, velocity is equal to frequency times the wavelength. Okay. In this example, the wavelength, the length of from crest to crest or trough to trough would be 23.4 meters, and then there would be a frequency of 103 hertz, which means that there's 103 cycles in a 1 second time period. So you would multiply 23.4 meters, which is the wavelength, times 103 hertz, which is the frequency, and that would give you the speed of the wave. Again, you're going to need a calculator for today. So 23.4 meters times 103 hertz gives you a speed of a wave of 2,410.2. And again, meters per second would be the units that you're using to solve for speed of a wave. Okay, number 2 says the frequency of a wave is 4 hertz. Remember, the frequency is 4 hertz, which is telling you that there's 4 cycles in a 1 second time period, and the length of one cycle is 0.06 meters. What is the speed of the wave? So remember, speed of the wave is frequency times wavelength. Your frequency in this case is 4 hertz times a distance of 0.06 meters, which gives you a speed of a wave of 0.24 meters per second. Okay, number 3 is a little bit different. Number 3 says the period of a wave is 2 seconds and the wavelength is 8 meters. What is the wave speed? Well, if you remember back to last week's notes, the period is the time that it takes to complete one cycle. So 2 seconds is the time that it takes to complete one cycle. And if you remember, frequency is equal to 1 divided by the period. So I need to solve for the frequency first before I can solve for the wavelength. Remember, period is the uppercase letter T. So the period is 1, or the frequency, I'm sorry, would be 1 divided by 2. So your frequency would be 0.5 hertz. And then your wavelength, they told you, is 8 meters. So the speed of this wave would be 4 meters per second. If you're needing to review the formulas from last week for either the frequency or the period, or to remember what they are, you can always reference last week's notes on this. So knowing this, you can go ahead and solve for problems 1, 2, and 3. And then you can also manipulate the formula to solve for either one of the variables that you have. So if you cannot manipulate the formulas, okay, your formula to solve for frequency would be velocity of the wave divided by the wavelength. Okay, if you're wanting to solve for the wavelength, okay, it would be velocity divided by the frequency. You can go ahead and solve again for problems 1, 2, and 3. Please make sure that you write those formulas down somewhere so that you have them for reference. Remember, speed of the wave is equal to frequency divided by the wavelength. The frequency, if I solve for the frequency, it would be velocity divided by the wavelength, and if I were to solve for the wavelength, it would be velocity divided by the frequency. Remember, frequency is measured in hertz, wavelength is in meters. If it's not in meters, you're going to have to convert, and if they're giving you the period, the time it takes to complete one cycle, you're going to have to use the formula period is equal to frequency is 1 divided by the period in order to solve for the frequency first, and then you can plug it into your formula. So go ahead and solve for problems 1, 2, and 3. And that would be the end of our notes for today. So remember, it was just a review on the different parts of a wave, and then now we just added how to calculate the speed of a wave. If you have any questions, please make sure that you email me, and have a great day.